Great pleasure to have with us Professor Nilmani Mathur from TIFR, and he will be talking on a few novel aspects of modern physics, and it's a vast area as you will see, but means I think that Professor Mathur will tell some very interesting aspects of this side to all the students, so that you can understand some of our students, as they are very new to this subject. So I think they will get some very new exposure to this thing. And I to inaugurate this session, I would ask our principal Professor means Swami Kamalasanandaji Maharaj to give an inaugural lecture, and then we will ask our head of the Department of Physics, Professor Ashok Kumar Pal, to introduce Professor Nilmani Mathur to the audience, and then we can start the session. Over to Swamiji.
Respected Professor Nilmani Mathur, the Professor Department of the Physics, TIFR, Mumbai, and my dear colleagues and my dear students present in this platform and other platform, YouTubes and other. So it is a great pleasure for us that we have Professor Nilmani Mathur, this very senior professor of the Department of Theoretical Physics, TIFR. And because he is actually so senior in this field, in this physics field, and he also a good teacher, and like also he also a good students also. So it is a very great opportunity for our students to interact with him after this after his talk. So I am on the very outset, I expressed my heartiest regards and also thanks to Professor Nilmani Mathur on behalf of the college, on behalf of all the students, faculty member, for his kind consent in this webinar as a resource person. And I tell the students that after the talk, you wholeheartedly interact with him. If you do not try to, then you can talk in your Bengali language also, because he knows Bengali. So he can easily interact with you. And it is a great opportunity. Don't miss that after talk you interact with him, so that you can learn many things regarding physics and its approach. So with these few words, I once again thanks Professor Nilmani Mathur, express my regards also on behalf of the college, and also thanks all the participants, those are present in this beautiful afternoon in this webinar. Thanks all of you. Thank you.
Thank you, Maharaj. So now I would request Professor Ashok Kumar Pal, the head of the department of our physics department of RKMVC College, to introduce our speaker, and then you can just start the session. Thank you. Over to Ashok Pal, sir.
Good afternoon to everybody. This is a very happy moment, and we have with us Professor Nilmani Mathur, Professor of Physics in Department of Theoretical Physics at Tata Institute of Fundamental Research. I feel really honored to introduce Professor Nilmani Mathur with our audience, and would like to express my deep gratitude to Professor Nilmani Mathur for taking time out from his busy schedule and being over here to deliver a talk on an interesting, modern, challenging topic entitled A Few Novel Aspects of Modern Physics. On behalf of the principal, organizer, and all students of this webinar, I cordially welcome Professor Nilmani on today's national webinar on modern physics arranged by my department, that is Department of Physics, RKM VC College, Rohora. As I have gathered from NET, Nilmani Mathur obtained his BSc in 1990 and MSc in 1992, both from University of Calcutta. He obtained his PhD degree in nuclear and particle physics in 2000 from Rensselaer, USA. He worked at several renowned institutes during his postdoctoral period, like TRIUMPH, which is basically Canada's Particle Accelerator Center, University of Kentucky, Thomas Jefferson National Laboratory, USA. His research area lies in the interface of quantum field theory, high energy physics, and large-scale high-performance computing, mostly to study the properties of elementary as well as composite subatomic particles. Professor Nilmani has published numerous papers in international journals and conferences, including physical review letters, etc. Anyway, apart from all these, I could not resist myself to introduce Professor Nilmani Mathur in other way. He was my classmate in MSc course in Rajavaja Science College during 90 to 92, and we too also lived in the same hostel for 2 years. Down the memory, I recollect those happy moments, feelings, and togetherness with Nilmani. Once more, I extend my warm friendship to him. We all eagerly waiting to listen from Professor Nilmani, so I would not lengthen my speech anymore and request Professor Nilmani to start his lecture, and I just over the microphone to Nilmani. Please, Nilmani.
Okay, can you hear me? Can you hear me?
Oh,
all?
sure.
Yeah.
Sure.
Okay. Yes, it is a great pleasure to talk in front of you, and I very much thankful to Principal Maharaj and Ashok, who is my classmate, and you may also may not know Principal Maharaj is also my classmate, and it's a great pleasure that I could come and talk in front of you. When Principal Maharaj contacted me, I accepted that yes, sure, I can talk with the students, and that's the what we should do actually most of the time. And thanks for all the invitation and a nice introduction by Ashok. And let's proceed. And so I change a little bit title of my talk. So talk title, a few novel aspects. So not novel all aspects, but few novel aspects. Okay. So before giving this talk, let me tell a couple of things. That this will be an informal discussion type talk, mainly for students, and it is not a formal talk that we generally give in seminars or various places. So I'm not discussing all important new aspects. So you should not assume that these are the what I am discussing. These are the all. There, I'm discussing as according to my understanding, which are now state of the art, or will be very good for the students in futures. Let's say next 10-20 years. Certainly, there are other important aspects which I am not discussing here. They are not my works. I mean, these what I will discuss. These are not my works. My work, I will discuss a little bit, but it will be just a survey to bring to our attention some of the important developments in modern physics. As I was telling that, what will be like in next 10-20 years, what will be the main topics as I understand. So no detailed discussion here. Detailed discussion can be done later. And relevant references I haven't added properly as they should be. If you need slides, I can add and give you the references altogether. Having said that, let's start this talk. I start with something called a quantum tree. I was attending a symposium about 10 days ago, and there's Michael Shipman, he's a very renowned nuclear physicist. So he draw this um, quantum tree. It's the quantum tree. It started at 1920. So I forgot to put the year around 1920 at the beginning. Can you see my cursor? Hello. Hi. Can you see my cursor?
Yes, sir, we can see the cursor.
Okay, so this quantum tree started around 100 years ago, and it flourishes all over. Um, it goes to nuclear physics, condensed matter, quantum field theory. So these, as deeper the color, it started earlier, and greener are the new things, as according to this Mikhail Shipman. And there are connection between different branches also. You can see the connection, and I think one can add more connection from one branch to other branch. So it has nuclear physics goes to particle physics, and then astrophysics was there, and astrophysics there is a connection. And then in 1973 quantum chromodynamics started. It just became a separate branch. It went to something called the lattice field theory, the subject of my area actually here. And then there are various other things like supersymmetry, and then high energy physics, some other branches. There is a gravitational theory, there is string theory. String theory has various branches like the swampland, which is now very, very interesting. And then astrophysics, cosmology, all are like, there's a huge number of branch took out from 1920. And of course there is condensed matter and quantum chemistry, and then there is material science coming. I will talk a little bit about all these how important are these material science, nanophysics are there. uh, and many are connected through now computation, large scale computation. And machine learning is starting to connect many of these branches, one branch to other branch. So these are the quantum tree, and these will be like that. Green color things are newer, and they will dominate in next 10 20 years. um, and I will not discuss all of these. I will discuss some of these things, and which I think will be more important. And let's start with that. So this is the grand picture. We know that there are four forces of nature. The one is left corner, right, a top. This is the gravity force, and then the electromagnetic force, and then below right corner is a weak force, and top right corner is the strong force. A strong force provide the stability of matter, like proton, neutron. That's why they are there. There is a hydrogen atom because of that. And universe, actually basically the visible universe built up because of that strong force. So I work in this area of strong force, and that's something called the quantum chromodynamics. I will not discuss much about that, but if student or some other time I can give a separate talk on these areas of physics. But today I will discuss some particular combine some areas. Okay, first start with the astrophysics and cosmology and gravitation. So I think the astrophysics, cosmology, and gravitation is the field now, and there will be a huge number of experiment going on. Also, it will be in next 10 20 years, and huge number of data are coming. And since the data are coming, because physics basically in the experimental subjects, in the experimental going on, new data is coming, and so theory will flourish, new discovery will come. So this is a plot of the temperature map of the sky. Most of you all know about it. Is the cosmic microwave background, CMB. So it shows the temperature of the sky. The blue basically the blue is the like temperature is small, and the red color temperature is higher. But more or less you can see the uniform. There are some distortion here and there, but it is pretty homogeneous, isotropic, and almost flat. So universe, as you know, people because there is a Planck survey took place, and they concluded the data taking after many years in 2012, and they came out. So this is basically what they do. They go to the sky through satellite and found out the temperature distribution at very low energy, like the microwave level, and they found that everywhere this energy is there. These photons are coming from everywhere, but with the same temperature. So you can calculate, you can get this photon and detect it, and then map it, and it is totally everywhere, as you can see, everywhere. And some places it is bluish, mean temperature small, that means there are may not be many particles there. The photons are not coming, and the red, there are too many are there. But you can one cannot say that this is not uniform. This is basically uniform, but there are lots of there are some non-uniformity also there. Now, from the data analysis, which is subject by itself, and there are huge computational effort is needed to do the data analysis. And from the data analysis, they found out the observable of the universe is close to isotropic. The universe has recombined Z. Take it Z as basically the redshift is very long distance. Z basically means it is a distance away. Very earlier they recombined and started to become ionized at some times. I will discuss a little bit on that. The geometry of the universe is flat, which is very important. It is not that some spaces is curved, some places it is the other way. It is flat basically. Both dark matter I will discuss and dark energy are required. I will discuss what are those. Unless we put those, we cannot get this type of distribution. And then gravitational instability is sufficient to grow all of the observed large structures of the universe. There is very little distortion happened. That distortion you also see in the map, and that was sufficient to make all these structures. And people claim there may be some topological defects at the beginning, but it was not there. So they are synchronized super Hubble modes. You don't have to understand, but this is some other type of modes which is expanded rapidly earlier. The initial perturbation are predominantly adiabatic in nature. The primordial perturbation spectrum has a slightly red tilt. These are the conclusion. And the perturbation had close to Gaussian. As I was telling, these it is uniform, so it is Gaussian type, some perturbation, whatever is there. But basic things, it is homogeneous, isotropic, and whatever direction you see, it is there. These backgrounds is there. Now, as we understand from this type of measurement that there is a Big Bang happened, because it is everywhere, this spectrum, you cannot explain otherwise. That is called the dawn of time. And then the tiny fraction of a second, I've discussed a little bit more. It expanded like 10 to the minus 32 second. It expanded from almost 0 to 10 to the 25 times. That small time it expanded very rapidly. That we call inflation. It needed, because unless we use this type of inflation type of model, these are, I mean, nobody knows whether that happens or not. But to explain this type of Planck data, you need an assumption that the universe expanded from these infinite energy 0 point to everywhere. 10 to the, as I told, in 10 to the minus 32 second, it rapidly expanded to 10 to the 25 times. And then I will tell goes to the recent times, which is about 13 to 14, 13.7 billion years now universe age. One can calculate from the map also. So as I was telling, that at the very beginning it expanded rapidly, and that was the cosmic inflation ends. Unless we assume this inflation, we will not be able to explain the experimental phenomena. But it is not proven that inflation happened. There are many things need to be checked, and that's why the new experiment will come, and a student like you can join and can say whether this inflation happened or not. These pages is basically the full of quark gluon plasma. What does it mean? It is quarks gluon. They didn't form any particle at that time. They were just like a plasma. You know the plasmic state. So the quark and gluon, they make it shoot, and that didn't have any viscosity almost. They're just flowing of this rapidly expanding universe. And then when the temperature became about 153 MeV, 150 MeV, then what happened that these quarks and gluon, they form these particle called the proton and neutron. And so as you know that when one phase to other phase it goes through like a phase transition, like the water, if you heat it, it goes to vaporized, there is a phase transition, or ice to water, that also a phase transition. So these type of phase transition happen, and that phase transition we can actually calculate on using like my field of study in quantum chromodynamics. You can calculate, and this temperature that I told 153 MeV is a huge temperature. So that temperature we calculate from these type of large scale numerical, and we believe it is correct, and nobody will be able to check it. But experimentally now it is possible to get some hints that that it actually happened. And those who know about phase transition, this phase transition is not first order, its phase transition is not second order, it is like a crossover. It is very, very weakly type second order, it is a crossover transition happened. And then what happened that it was full of these particles, proton, neutron, then electron, neutrino, everywhere there, and they couldn't form a bound state because temperature is very high. But as the temperature goes below about 1 MeV, the miraculous thing happened. At that time, deuterium formed. The proton, neutron, they were converting to each other, and they were in equilibrium, and wherever they tried to bound it, at high energy photon, neutron, neutrino, they are just dissociating them because they are the equal energy, so they couldn't form a bound state. But at 1 MeV, what happened is that the deuterium, the proton and neutron bound state, the first form, and that has to be because deuterium binding energy that we can calculate in the experiment is about 2 MeV. So unless it temperature is universe in terms of, imagine from the first to second it takes a tiny amount, but the second to third it is long amount. So that time it took to form the deuteron, and once deuteron formed, then started atoms, and this which is called the barrier, which is called the Big Bang nucleosynthesis. One can calculate by hand those cross sections, and people you know that Hans Bethe has done those calculations and got Nobel Prize also, and he showed us how to calculate those, and those matches with the experiment. Then once the hydrogen atom forms, then there was a time when these there's a dark period because universe was opaque. The light couldn't come out, the photon couldn't come out because it was like so dense it couldn't come out. But as the universe expand, the light could come out because the particles are not like very dense, so light could come out. And then this hydrogen atom, and they could form by gravitational pull, they could form the stars and galaxies, and here we are. This is just a brief history, and from that map actually we can get all those information, and so a huge physics involved to get all these inference. And some are maybe speculation, some are actually true. Now this is another plot. Since I discussed already all of these, I should not discuss all of the, again. One thing I forgot to tell, that at one point of time, the quark gluon and also the electron, they are the same type of electric force was interacting at this very, very small scale. But then the phase transition occur, as I told, these quarks became the hydrogen atom and others. So these are again the story of the universe. Now we have to make a model out of that. The cosmologists make a model out of that. So model is basically very simple. It's called the lambda cosmological model. There is a lambda. I have to tell you what's that. So you can think about, let's say, in the expansion rate. So universe is expanding, that we can detect that. And the expansion rate, let's say A, which is related to redshift, like things are moving away, we can detect it. And there is a parameter, well-known Hubble parameter, a dot by a, the a like distance, a dot like a, and then one can write down these type of equation. So these is basically a like how fast it is moving away. So this is a matter term, it's a density of matter, and this is a curvature, whether you are flat or it is curved, so you have to put a term. And there is another term. So these can come from the Einstein's equation, 0 component. This is basically the first equation, and lambda is a constant which can determine like whether the universe will expand forever or will crunch, depending on the value of the lambda. And this is another Einstein. I didn't write the Einstein equation here. Einstein, from the stress of Einstein equation, one can derive this equation also. And here, what is showing that the rho density and the pressure P is related like this. And if the universe is expanding, so that means the P has to be, this is positive, then the P has to be negative. So pressure of the negative energy, P has to be a negative energy, because P be positive, then that it may not be positive this side. So this is basically showing that maybe some negative energy is expanding our universe. So that's people are claiming there's a dark energy. We don't know actually what is that, and I will tell how much is that. And then density parameter, one can there is three terms of their matter term and curvature term, and there is some unknown, some these expanding, which forces and expanding. So this term one can write down what is the density term, and then you can add them together, get a how fast it expand, and you measure it and see whether this is the correct value you are getting or not. Right now there is a huge controversy, actually puzzle going on. The if you measure these Hubble constant, I will discuss later, Hubble constant at from some object, it is giving some value. If you measure from this CMB, it is giving another value. So people are claiming maybe there is a new physics going on we don't understand. I will show the plot and then you will understand that. Okay, so what does the universe consist of? From that plot where I showed the CMB plot, it consists of something like that. There is a luminous matter, stars, galaxies, gas. It's full of gases everywhere. You will see this hydrogen. Gas means it is this hydrogen, molecular hydrogen, nothing else. But that constitutes a very, very tiny fraction. And then there is a huge matter density fraction is there, which I will discuss. Okay, let me show the plots, and then you will understand. By the way, I can actually, one can derive what is the age of the universe by solving just some trivial equation. We can come back to here later. The universe age is 13.78. If you know these parameters, sigma omega, sigma matter, sigma curvature, everything. Okay, so what you know from this map is like this, that our matter density or energy density is basically most of the part we don't know, but it is expanding. So we know that there is a gravitational pull is going on. So we know what is that part, and there is a huge part we don't know nothing about it. The visible part, it constitute only this very, very tiny section, and it had like the galaxy, stars, everything 0.5%, and the heavy elements is even less. And then free hydrogen, as I was telling, the gas everywhere. Where if you put a spectroscopy, like spectroscopy item, and see whatever in the universe, you will find out everywhere there is hydrogen atom in some form, molecular form or some atomic form. And these galaxies everywhere, the intergalaxies medium, there is hot hydrogen gas basically. But that fraction is also very small. And the most part, the visible part, most part is a dark matter. And I will discuss why it is necessary to have this dark matter. And then there is a dark energy, as I was telling, that universe expanding. From that data we can figure it out. All right. Now, why I will explain to you why there is a necessity for dark matter. You know, if you just solve this virial equation, two masses or the moving masses, just energy on one side and the kinetic energy on one side, you can get these orbital speed, the v, gm over r, And this is basically Kepler's from second law. You can derive it, and you can see that these goes very well. These map very well, like the orbital velocity and distance. All the planets, it goes. The planetary motion is basically like that. But if you go to the real data, this is some real data. So this is again the distance and the velocity. So these are the real data. See the difference between that. Difference between yeah, the difference that is 1 over r going, square root of 1 over r is going, but here it is going, and for some of them it is actually flat. It goes like that. Some of them goes a little bit higher. We expect that this will go down, but it is not. So what does that mean? So that means that the planetary motion that we think is not working. And how can these go up? Because if there is an extra mass, then the velocity will increase. For gravitational interaction, velocity will increase. Then you can figure out that these you can put some mass number, like value, how much you need to put, and then feed the data, and that gives this value, that 25% or 26% that I was talking, the dark matter. Without that you cannot fit it. So that is one proof, and you can do it numerically also. There's a large scale simulation goes on, like n body simulation of universe. So you can put like a jillions of particles in a box and calculate an n-body simulation. So unless you put the dark matter, you cannot get this type of flat curve for the velocity plot. This is one example that dark matter has to be there. And there is then another example is the gravitational lensing. So gravitational lensing is a bending of light because of the matter, because we know from the Einstein theory and the gravitation that the huge body bends put the curvature of space. So when the light has to go through the space, so if it is bound, then it will either bend like a lens. Light bends, so it will also bend. There's here the example also. So there is a matter here, light is coming, so it will bend. So whatever you want, you will see. You're supposed to see these, but you will see there. So that means here there is a matter, and you put some instrument there, like instrument like a satellite instrument, and see there is no matter here, like no signal is coming, like no photon is coming, no infrared radiation, nothing is coming, but still the light is getting bent because you see the object there. So these shows, like this is a real picture, like this is light bending. It's supposed to be here, but it goes down, goes there. So it shows that there must be something in between. So this is with the intergalactic medium, the huge dark matter is there. That's why light gets bent. So this is another example. And then this is one example of from the CMB plot. One can derive, like say at each point I put a temperature, this theta, and you can, and then what we calculate, one can calculate the theta one point to other point, some correlation function. You can calculate 2-point correlation function each point to each point, and then plot as a function of. So then since you are putting in terms of the harmonic, so it will like a spherical harmonic, and you can put a direction, and other direction is how many at each distances, how many for each spherical harmonic, basically at each distances how many particles you are getting. And that can give you this type of plot that called the spectrum, power spectrum plot, and it shows some type of fluctuation. And one can relate this type of fluctuation with this lambda CDM, what I talked, the model, and can fit it the data with that model. And in that model, if you do not put the dark matter, these extra matter density, then you will not be able to get these type of fluctuation, the second peak particularly, and also it will decay down differently. So that also shows that the dark matter has to be there. And then there is the interesting something called the bullet cluster. This is a picture many of you might have seen earlier. So what it showed is that there is two clusters. So these are the visible matter, which is a pink color, and the blue color you cannot see those through like any our instrument, like for example some infrared signal or something, you cannot see that. But So these two cluster, the bullet means this is like a bullet type of shape. That's why it's a bullet cluster. They two cluster, they bang each other, they cross each other, and the matter they interacted. But these blue things, which can be detected from the gravitational pool, they don't show. They are just passed through each other. They don't like no, they banged each other, but they don't like give any light or any other wavelength photon. So that means they don't interact like our real like two particle collision that we know. Let's say hydrogen atom electron is coming, hitting it, and then photon is coming out. Not like that. So it's a different type of matter, but they are there. So there are various examples of people, experimentalists have found out that help us to conclude that this is really some extra matter is there, and that is the most of the part, and we don't understand what are these. So this is an outstanding problem now in physics. What are these matters? What are the dark matter? They don't interact with our regular matter like proton, neutron, or any other electron. They don't interact, and since they don't interact by our known forces, this electromagnetic or strong or weak, they only interact through gravitation. And so you have to be very like careful if whether you are detecting it not, because signals, the gravitational signal, gravitational force is very small. um, and people have tried to see this dark matter in our solar system. Nobody found anything in the solar system that is a dark matter, but still in the large distances they are prevalent everywhere. Now I will. There is another interesting thing. Everybody now know that we experimentally discovered the gravitational waves. The gravitational wave is an invisible yet incredibly fast ripple in the space. Is Einstein equation. Einstein shows us that the space will be bounded by the gravitational forces, and gravitational waves travel at the speed of light. These waves squeeze. Let me show a video, YouTube video. You might have seen this thing, but those who haven't seen, let me show that video, and then it will probably be okay. Now, how to show this video? Hello.
Just this air portion,
Yeah.
you
So now
you
I have
just select.
stopped. I have stopped sharing, and now I will
Yes.
uh, mm,
Then you
share
share and then
screen.
optimize for motion and video.
Optimize. There is no optimize. There is a
The
screen and
left,
application.
top left combo box is there.
Top left.
Optimize for text and image. Then you select, just click and then
Just is coming screen, nothing else. Let me see whether it can. Um, Video coming. The YouTube video is it coming.
just 1 second. Sharing.
Hello.
It is sharing, not yet coming. Sharing.
I see.
Just click. It is you click and the sound or anything it comes.
There is no sound, but it is. Is it coming?
Is it coming? Coming.
Okay. So you can see that uh, mm, uh, two massive bodies. So these could be black hole. This could be other massive bodies like neutron star. They are in gravitational force. They're attracting each other, and because Einstein theory tells us that there is a bending between each other. So when the gravitational waves are coming out, and these waves are going everywhere in this universe. So when the two huge body collide each other. Now. Let me stop that one, and then I will this is stop sharing, and then I will share again to my talk. Sorry for this. Yeah, can you see my PowerPoint again?
It's coming. It's not visible, but it's sharing. Yes, yes, it is visible.
Okay, so that cartoon picture was showing that two black holes actually are colliding and the gravitational mm, waves are coming. And in Earth, we are actually put two detector. I'm not going to details in the detector because I also don't know very well of this experiment, but they can detect these signals. And you need, because of the background, the constant background, you need some type of interference, and it is plotted in this side time versus these interference strain, which is very extremely small, but that's why the need the experimental is precise experiment that I will discuss towards the end. You won't need that, and that is oscillating signal, and when they merge, they put some type of tube signal. Very the frequency has increased, and then they dissociate and become one. So that's why the gravitational two massive body they collided to one. And after that discovery, the discovery got Nobel Prize. After the discovery, there are many also got discovered, not only from black holes, from other objects like neutron star. So this is brings to neutron star. So neutron star are some of this fascinating object of the universe. Why I'm talking about this, because these are the subject will dominate in the next few years. So this is a cartoon of the neutron star. It has a huge magnetic field. It is pulsing. Pulsing means it is emitting light in some frequency. It is rotating, and the rotation can give very precise period, and the light will come out. And this shows the magnetic flux line. And these are cartoon, not any real picture, because it's far away and it's extremely dense. We don't see how is neutron star forms. This is a cartoon again, but this is speculative cartoon, and one can understand why these are happening. So this is let's say star, and it has an inner core. Inner core has hydrogen atom. You know how the star formation takes place. We know very well. And the inner core, the outer core, and when the burning like fuel lost, like hydrogen atom are not burning anymore. The hydrogen atom burning actually push the light outside and force outside. That's why we get light, and sun is coming, and sunlight is coming, and hydrogen atom is burning there. So when it stops, then it will be gravitational pull. It will whole the big star will pull to a very tiny fraction, and then because of gravitational force, sudden some shock wave will come out, and one can detect that shock wave actually. And then matter will be the matter layers compress and merge. They will compress, and then at some point of time, what will happen, the outside core will just fly away, because of the shock and instability, they fly away, and it will be a very tiny, this huge star. From there it comes to this small, and the radius is about, maximum radius could be 20 kilometer, like that. From the, this how big is the sun, and these stars could be even bigger than sun. Actually it could be 2 times bigger than sun. And it goes like 20 kilometers. So how dense can it be? Like in one teaspoon will be like a Mount Everest. And this is a fascinating object, and we don't know anything like what is inside. That's a challenge of modern physics. What is inside the dense star, the neutron star? And the neutron star get denser with depth. Outside we know. I mean, how do you know all these things that I was telling? The experiment gives us some signal, and you have to make a model, and that model fit the experiment. That means that is correct, and through that we know all these things. So neutron star get denser with depth as you go towards the core. Although people have found that good sense of the composition of the outer layers, the what is outside, we don't know what is inside. I will tell what is outside, inside, what you know. The core inside, people speculate that core actually had some maybe a quark matter is there, like the quark gluon plasma could be there, but its temperature is extremely low. they are not burning anything. So its temperature is very low, very, very dense matter. It is not the Big Bang like quark gluon plasma. It is a quark, could be quark gluon plasma, but very, very low temperature, high density, low temperature. And they could be in superfluid state and or superconducting state. And actually, there's some experiment will go on in something called the electron ion collider in USA 10 years from now, and that will speculate some of these things. Also, the FAIR experiment in Germany, they will speculate some of these things. But there is a quarks. There quarks are there. It could be like Bose-Einstein condensate. There could be other particles inside there. But basically, we don't know much about that. So there's a huge field where people can work, and it will dominate some of the time. So as we know it, so there are these. Okay, how am I doing with timing? Maybe. Okay, I will be fast a little bit now. So this is a cartoon picture. What is inside? As you go, the outer crust actually ions and electron, and then if you go deeper, the electrons, neutron, nuclei, and then if you go even deeper, the neutron, proton, sometimes Fermi type liquid, Fermi liquid, they're there. Few percent probably Fermi gas, and there could be quark gluon plasma also inside it. But these are all speculation. I mean, we don't know. What we know, the magnetic field, the magnetic is very strong, and some of the magnetic is strong. Some of the magnetic field are strongest in the universe, like the magnetars. So these are some type of neutron star with huge magnetic field, and that could be 10 to the power 18 Gauss also. Even could be higher. And we are doing some, in fact, some calculation in the high magnetic field. Maybe the proton and neutron, some transmutation can happen. Like we know, neutron cannot go to proton because there is a mass difference. But if you put a high magnetic field, the magnetic energy will increase. They increase the mass, so neutron can decay and can go to the proton. Of course, you have to do the beta decay and electron positron emission. All these things need to be done, but it can happen, and some of this calculation we can do in computer also. Okay, so this is something called the equation of state of neutron star. That is behind, everybody is behind it. So what is there? People can plot the energy density and the pressure, and the energy density. And from nuclear physics calculation, one can do calculation at this corner and that corner, but we don't know anything about in between. Now, this plot is from this plot, left plot, one can actually do the right plot, which is mass, radius of mass, and radius of neutron star. The mass is this axis, and neutron star this is mass in terms of the solar mass. And these are all the theoretical points, and there are because of the huge uncertainty here, there is a huge band. But now new experiments are coming, and this gravitational wave detection also is telling most of the neutron star would be like these type of band. Like in radius could be maximum, let's say 14-15 kilometer, and they can be maximum 2 or a little bit higher, 2.5 maybe, not 2.5, 2.1 to solar masses. There is no neutron star like this corner 2 or 2.5 or 3. So lots of equation state will go out. Theorists are trying to get like what could be the best equation of state, and the plot of neutron mass versus radius, how it could be. So this is one example that will be sustained for some time, and it can bring also Nobel Prize at some point of time. Now, why I'm discussing all this? Because there are 3 experiments that India is participating, and this is like a $1 billion project, and India is also spending a lot of money. This is a mega project by Department of Atomic Energy, Department of Science and Technology. So this left corner is a LIGO, and India will be participating something below that is, it's a LIGO has detected that obviously gravitational wave. These are the 2 arms that I showed. And but as you know that this works in the interferometry. That means you need the many signals at different places. Then the signal will be much better, and signal will 10 to the minus 21, like that level. So India is participating in this, and somewhere in Maharashtra, India will also build a detector like LIGO, and this is called the Indigo, and then the square kilometer array. These are the all telescope. These telescopes are there. The square kilometer array. So this is Australia and also in um, South Africa. So there are lots of these radio telescopes are there, so they will detect in the early universe what is going on. Before the dark ages, nothing can be known, but after the dark ages, when photons comes out, that can be detected. One should learn that the light will be very faint, but there are some signal can be detect easily, so that which is called the 21 centimeter line. You know that the hyperfine splitting in the hydrogen atom, that when you put the spin and orbit coupling, the spin is not spin and spin interaction, there is a hyperfine interaction between two spin, and that can split two energy level and one energy level to other. There can be transition, that for hydrogen that transition is 21 centimeter, and that signal can come whenever the photon was started, like at the very early stage, and that photon, but it is 21 centimeter, that means microwave level, and detection will be difficult. So that's why you need so many of them. Actually, the GMRT that we have, TIFR has at near Pune, so that also try to detect some of these, but this will be much bigger scale, and India is participating on that. And then there's the TMT. This is an optical telescope, 30-meter large telescope. T is 30-meter telescope. India is participating, and that will also give signal from the early universe, and we will know whether all the speculation that I was talking is right, or some of this thing will be known.
Excuse
So,
me, sir.
yeah,
So I think the means presentation has freezed. Means
is it
the
coming?
gravity. It is coming. The gravitational wave page is only showing, but if you are changing, means we cannot see any. If you are
Oh, you didn't see
changing,
anything on the Neutron star?
no, that gravitational page is actually there
Oh, you should
on
have
the.
told me. I got far away.
Yeah, means
You should have stopped me
yeah,
and
yeah,
told
yeah,
me.
yeah. Okay. Now it's fine.
Please actually this slideshow mode, you go for slideshow mode so that the screen would be larger.
Can you see something?
Yes, sir. Yes, sir. The neutron star page is coming visible.
Oh, you should have told at that time. I described a lot of things there, like how the neutron star is forming. Um, can you see a plot?
Yeah.
Okay, I can come back here again, like how a big star going to the small star. You should have stopped me and told me that we're not able to see anything.
Actually,
And what is inside the neutron star I described. So this is the fascinating neutron star picture. We can come back here to the student again, because they may have not seen it probably. And then what is inside I showed, and then the equation of state of the neutron star I had shown. Like this type of picture, we cannot get three high mass neutron star that we know. And then can you see this LIGO picture, all these? Hello?
yeah. The LIGO picture was visible.
No, now
Now,
there is four separate screen is there. LIGO SK, LIGO India, TMT. Can you see that?
no. That is not visible. Means
Okay,
somehow it is freezing somehow.
let me stop
I don't
it,
know.
and then let me stop it and share
Yeah.
again.
It's now coming.
It's coming.
Yeah.
Can you
Uh,
see the
you
LIGO
you
S?
please you may make it slideshow mode, slideshow mode.
This is in slideshow mode.
But here not is it is coming slideshow
Okay,
mode.
let me stop it, and again I will.
Maybe some problem. Yes, stop again start again share.
Okay, stop sharing and then share again. I think the video makes the thing horrible, so I will not show any video.
Uh, uh, now you now select this text mode. Text mode.
Can you see these LIGO, SKA?
It's just coming. It's not visible yet. It is sharing. Yeah, that part has come.
there is a left corner LIGO, top right SKA. Can you see that?
Yes, sir. Yes, sir.
Okay.
Now,
So
now it's
yeah, I'm sorry that this happens. Is these things are moving now,
yeah,
or it is
means
not moving?
are you changing? Means
Yeah,
I
I'm
can we
changing.
can. Oh, but it's on the that LIGO SKA page.
So is that what is happening? Some connection
And
problem or?
I think you select this video mode still now. You now actually select the optimize for text and image option. Then I think this will work.
Optimize for, okay, I stop sharing again. I share has screen and application,
You
and I
know
go,
this top portion na share content below share content one option is there optimize for text and image.
actually the problem is that I didn't download it. I am using from like browser. Is that
Oh.
whether that's
I think that's why that there is a lag. Uh, maybe, but you can carry on. Means
no, I mean, if you don't see, then that's a
it is
I mean,
taking time, but it's coming. Means if you change, I think it will come after some delayed time.
so
That's what it will happen.
what screen are you able to see now?
Let it come. Don't know. Let it be there, and we can say. Yeah, this is the LIGO page. Means
Okay,
four
the
square.
now next page, can you see the what do we envisage to learn?
It's not yet there.
What screen are you seeing? Maybe I stop my video. Will that help? Well, let's see.
Yeah, yeah. Now that what do we envisage to learn? That page came.
Okay. But
Can you
why
change
it's
one more? Then we can just see whether it
okay?
is
Okay.
changing.
I changed to another one.
Yeah, yeah, yeah. Hubble puzzle.
Yeah.
Yeah, yeah, yeah. Now it's coming. Means I think you can
Okay.
carry on. You can
All
carry
right.
on.
Okay. So, what do we envisage to learn in big pictures? We want to learn the origin of the universe, more proof of the Big Bang. What is the fate of the universe? Like it is going to, it is crunching, or it will be forever expanding. What is dark energy? What is dark matter? So these are the new thing that will be dominate in next 10, 20 years. The formation, structure formation, there is huge magnetic field. What's the origin? The structures of black hole, including primordial one, neutron star. The stellar astronomy is a flourishing field. And then the planetary astronomy, like Earth-like planets, there is a huge study also to find the extraterrestrial life. And then the gravitational physics, the eternal, whether there is a quantum gravity or not. Okay. Uh, Now I will not discuss the Hubble puzzle. Basically, there is a discrepancy between various measurement, and people are telling the Hubble constant may not be like one. They may be changing. Okay, but let's. I will discuss the other field, the nuclear physics. Okay. Can you see the nuclear physics screen? The setting the scale, that screen. Hello.
Not yet there. That Hubble puzzle is there all still.
No. What should we do? Because we have a couple of other subject to discuss.
Yeah, setting the scale that has come now.
Setting the scale has come, so it is getting slowly.
Yeah, yeah.
So we are discussing physics at the very top, which is at megaparsec level, and then we come down to some other level 10 to the minus 15 to 10 to the minus 18 meter, like quarks and gluon. So that's the world of Japto world. Japto is 10 to the minus 21 actually. So there the 10 to the minus 15 to starts the nuclear physics and particle physics. Okay, so this is the standard model of particle physics. Can you see the screen? Standard model of particle physics.
No, no, it's not there still.
Should I download and then?
I think what you can do means when you intend to change, you do it previously from that time, and then it will come at that point. I think.
This is terrible.
Otherwise,
No,
yeah, yeah. But what else can be done
yeah,
now?
yeah. Now let's.
Standard model of particles has come.
Yeah, yeah. This is now visible. Standard model of particle physics is
Is
now
there
visible.
some internet problem, or this is something? This, do you feel this problem, or this is the first time?
It's actually this type of lag. It's unusual.
Yeah.
Maybe
Uh,
just you can carry on. Means
okay, okay.
it will
So
come.
this is the standard model of particle physics. This is like a chakra, and you can think about that Bodha chakra. So all the particles is given here, the fundamental particles, and which is there is quarks, the 6 quark, and then 6 anti-quarks, and then there are neutrinos, the 3 neutrinos, and then there's the electron, there's the muon, the tauon, these, and then the gauge bosons are inside it, like the photon, and the gluon. They're the carrier of force of the strong interaction, and then this is the Higgs boson at the center, which provide the mass of all particles, whatever the mass of all particles. So this is the standard model of particle physics. So it has elementary fermions, elementary bosons. Bosons are the force carrier, and this is basically written down on the right side, but this is basically this chakra, or all of them are there. Now I went to the next page, which is showing the strong interaction. Are you able to see it?
No, still not.
I think there is a probably see that video.
Yeah, yeah. It has come. It has come. It is there.
But is it the problem of that video? That's why it started. Whenever,
Maybe from there it started. So
why?
I think some problem of bandwidth maybe happened there, and it is continuing.
Let me stop share again, and then stop video, and then stop share. I'm putting. I'm getting out from my video and putting the screen once more. Did you able to see it?
It is saying that you are
Strong
sharing the
interaction.
content.
Yeah, so you can the student can think about what is the strong interaction. We know that when you add up the masses of constituent particle, it can give you the total mass. But if there is a lot of interaction, then the total mass could be different than the additional particles. So one side we have put these 10 MeV mass from the quarks, if you add up the masses of the quarks. But other side, which is proton, which is made of these 3 quarks, are about 938 MeV. One side 10 MeV, other side 938 MeV. So from where these 928 MeV masses are coming? This is purely like a strong interaction. So that means these protons are not made of these only 3 quarks. There is strong interaction there, as showing in the right side. This is a simulation we got from the lattice simulation, something like that. And we can actually explain the origin of mass, but through numerical computation, not through analytical computation. So this is an outstanding problem also, how to calculate the origin of mass, like this hydrogen atom or proton, from a first principle analytical calculation. So this is like this is like a millennium problem. If you can solve it, you will get $1 million. This is a strong interaction problem. Computationally, we are able to solve it, but not analytically. So this is my actually field of research. The next transparency I'm showing this lattice field theory, the continuum to lattice. Can you see that transparency, or it is still coming?
Yes, it is taking some time.
There must be something wrong. Should I join again and then?
No mention. If it helps, then
Maybe I can log out and join, and then that will be better.
Yes. It is good. You just log out and join. I think maybe the problem will solve.
Okay.
that slide has been.
Okay. Let me log out and.
Yes, please.
Where is the log out screen?
This cross one.
That red circle.
Yeah.
Where I think that will help you log out.
Sorry.
There is a red circle with the cross in the bottom.
Oh, bottom. Yeah. Okay. All right. Let me. Hi, can you hear me?
Yes, sir. Yes, sir.
Okay.
You
Let me start sharing again.
okay.
Can you see a screen? A top is written continuum to lattice.
Yes, yes, visible.
Is coming.
Yeah. It has.
Okay.
You can continue.
Okay, so what we do, we have a fundamental theory of strong interaction. We discretize that on a space-time lattice, and then solve a computer through computer, and then that can help you to get solve this problem of from where the mass is coming. So basically, so is the next screen is coming? Hello, is the next screen is something?
Uh, Still, we can see the continuum to lattice.
No, then there's the same problem.
Yeah, it has not solved the problem, I think.
Uh, One thing we can do, I don't know, I can send you some Zoom link, but then you have to, how the student will get it.
Yeah, that's the problem. Everyone got it by mail, I think. So
I think you if you can share me the mail, I can show this. So
Yeah. What can you see? Let
it
me.
is continuum to lattice computer.
Okay, so I think that's the problem. Um, mm, Maybe I will put a PDF file and send to you. Okay.
Yes, I saw it from my end. Then everybody will see.
yeah, that I think will be a better idea. Means you share the content and then principals may share it from his.
Yeah. I didn't know this WebEx is that. I have some Zoom license. I can, but let me send it immediately. Yeah.
Please.
Yeah.
Where is this extra? So it will take few minutes. You have to excuse me. Hello.
Yeah.
The student will be
No
bored.
problem.
Sorry. uh, this is,
No, that technical problem means
No,
happen.
if you have PPT, you can also share. PPT is more bulky file.
yeah, that's the problem. It is a very bulky file. It will
Okay.
not actually. I have to do through. Just hold on. Because it is a video, it will not go through email. Okay, so I have to make it a PDF. Somewhere it got problem. Okay, I need 5 minutes to set this up. Okay, because this laptop is not showing. Uh, I am just logging it out, and then we'll come back after sending you this. Okay.
Yes, sir. Yes, sir.
কল্যাণ,
হুম।
I have joined. নীলমণি কি বেরিয়ে গেছেন নাকি?
আরে ইয়ের প্রবলেম হচ্ছে ওই
আর আমি মাঝখানে ছিটকে বেরিয়ে গেলাম, ডিসকানেক্ট হয়ে গেল, কিছুতেই ঢুকতে পারছিলাম না।
হ্যাঁ আমি দেখলাম লিখেছিলে।
আমি তোমার হোয়াটসঅ্যাপে লিখলাম শেষে।
হ্যাঁ আমি দেখছিলাম কিন্তু আমার তো এখান থেকে কিছু করারও নেই আর কি।
না আমি জিজ্ঞেস
হ্যাঁ
করলাম।
আমি দেখলাম তোমার লেখাটা আমি দেখেছি আর মানে
তারপরে এখন ঢুকতে
প্রফেসর
পেরেছি দেখছি।
মাথুরের প্রবলেম
হ্যাঁ,
হচ্ছে যে ওনার ওই ইয়েটা ল্যাগ করছে আর কি, পিপিটিটা উনি যেটা দেখাতে চাইছেন সেটা
সেটা তো
ফ্রিজ
হ্যাং
করে
করে
যাচ্ছে
গেছিল।
মাঝে মাঝে।
হ্যাঁ, সে
হ্যাঁ
গ্র্যাভিটেশনাল ওয়েভে হ্যাং করে গেছিল, তারপর নিউট্রন স্টারে দিলে।
তো সেখান থেকে পরপরই ওটা হ্যাং করেই থাকছে আর কি বেশ খানিকক্ষণ। তো উনি এখন মনে হয় ওই পিডিএফ ফাইলটা শেয়ার করছেন মহারাজের সঙ্গে। মহারাজ এখান থেকে যদি করেন ভীষণ সমস্যা হচ্ছে দেখতে পাচ্ছি কেন।
আমিও প্রথম 10-15 মিনিট আমি ঢুকতে পারিনি আর কি। কিছু একটা অসুবিধা আছে এটা।
না, প্রথমের দিকে আধ ঘন্টা 40 মিনিট ভালো হয়েছে, তারপর থেকে জিনিসটা শুরু হলো।
হ্যাঁ, কিন্তু আমি প্রথম মানে 4টে থেকে চেষ্টা করেছি, 4:15 অবধি ঢুকতে পারিনি, তারপরে হঠাৎ দেখলাম ঢুকে গেল আর কি। মানে আমি ল্যাপটপ দিয়ে ঢুকতে পারলাম, মোবাইল থেকে ঢুকতে পারিনি। মোবাইলে যে লিঙ্কটা ক্লিক করছি, মোবাইল থেকে ঢুকতে পারিনি। ল্যাপটপে এসে তারপরে চেষ্টা করাতে ঢুকলো আর কি।
এটা হওয়ার কথা নয়।
আমি তো প্রাইমারিলি ঢুকেছিলাম, তারপর ঢুকে আধ ঘন্টা পৌনে এক ঘন্টা পেরোনোর পরে অটোমেটিক্যালি কাট হয়ে গেল, দিয়ে কিছুতেই ঢুকতে পারছি না, শুধু ওই রোল করে যাচ্ছে। তারপর ওই নীলমণির হয়ে গেছে, তোমার যে প্রজেক্ট করেছে একটা স্লাইডে হ্যাং করে রয়ে গেছে।
সেই তো।
গুগল মিট ফিটে এসব হয় না।
সেটা ঠিক নয়, এটা আসলে সেটা ঠিক নয়। আমি তো গুগল মিটে দেখি, আমার এখান থেকে আবার গুগল মিটে বেশি প্রবলেম হয়। মানে এটা ওই মানে যেদিন যেটার প্রবলেম করে, এরকম কোনো হার্ড এন্ড ফাস্ট নেই।
গুগল মিটে আমি এখন একদিনও প্রবলেম ফেস করিনি।
আমি তো গুগল মিটে প্রত্যেকদিন প্রবলেম ফেস করি, বরং ওয়েবএক্সে আমার প্রবলেম ফেস করা কম হয়, আজকে একটু বেশি হয়েছে। এটা আমার মনে হয় ওই মানে ডিভাইস উপর ডিপেন্ড করে।
না, আর তারপরে আমার মনে হয় উনি আবার এই
না, তারপরে ওই যদি বাল্কি ফাইল হয় এবং যদি তোমার সিস্টেম পুরনো হয়, তাহলে মেমরি সাপোর্ট দিতে পারে না।
কি জানি কি প্রবলেম।
কারণ কি হবে এখন?
উনি তো করছেন আর কি, বললো এটা শেয়ার করবেন
আছে
স্টুডেন্ট 37 জন মতো আছে দেখছি।
এটা টোটাল পার্টিসিপেন্ট
37 পার্টিসিপেন্টস এখনো আছে।
Start with how many were
টোটাল
there?
গোনা 30
টোটাল।
To start with কতজন ছিল?
44
50 দিয়ে গেছে। না না, আমি 50 দেখেছি তো একবার দুবার।
57 দেখেছি আমি।
হ্যাঁ, 57 লাস্ট গিয়ে।
অনেকেই বেরিয়ে গেছে।
হ্যাঁ, আর কিছু তো ডাইরেক্ট না ঢুকে ইউটিউব দিয়ে ঢুকেছে হয়তো।
উনি যতক্ষণ ফুল স্লাইড শো মোডে করছিলেন ততক্ষণ ভালো আসছিল, ফুল স্লাইড শো মোডটায়, কিন্তু যেই ওই একটা করে স্লাইড তখনই আটকে গেল।
তো ভিডিওটার পর থেকে আটকালো আর কি।
হতে পারে, কারণ বলছে যে স্লাইড শোই করছে, কিন্তু আমরা এখানে তো স্লাইড দেখছি না, আমরা তো পুরো ওই নাম্বার অফ স্লাইড।
প্রথম স্লাইডটাতে হয়ে গেছে, স্টিল হয়ে গেছে, হ্যাং করে গেছে।
স্লাইড শোটা আর করেননি, মানে প্রথমবার করেছিলেন, তারপরে আর করছিলেন না।
না, উনি কিন্তু মানে দেখাচ্ছে, কিন্তু এখানে সেই ভিউটা আসেনি। ভিউটা এখানে দেখাচ্ছিল, পাশে স্লাইড গুলো দেখা যাচ্ছিল। যাই হোক, 1 ঘন্টা হয়ে গেছে, উনি র্যাপ আপ করতে পারতেন। 1 ঘন্টার তো দেওয়া হয়েছিল।
হ্যাঁ, মানে এমনিতে জিনিসটা একটু লাউজি হয়ে গেছে।
I sent it already. I sent to Principal Maharaj's address.
Yeah.
Oops.
Now the slides are seen in truncated way.
The PDF.
The PDF time is coming in a truncated way.
I see.
Sometimes full view is there, sometimes it is in a truncated way.
Okay, let me log in and sorry, let me.
Now it is visible, I think.
No, now it is visible. We can continue.
I think you
It
can
is
continue.
visible.
Now it is fine. Now it is fine. You
Now
can
it is
continue.
fine.
You can continue.
Okay, let's then continue.
Which one?
So I am. I think there is if there is any animation that is creating trouble, probably. Where are you? What can you see?
What do we envisage to learn that?
No. Do you see something called QCD phase diagram?
No. This is
Let me try to share.
No, QCD, yeah.
now seen etc.
QCD phase diagram.
Actually, I stopped sharing. How come that is coming? Because
No, I think it is.
sorry.
This,
it is.
the slide shows QCD phase
Yeah.
diagram.
So that is you are showing, no? Or
Yes, I am showing.
so we will proceed like that.
Yes.
Okay. Or should I try sharing once more and see?
No, you start. You start. I think from this onward, when you tell, I can proceed.
Okay. All right. So this is like QCD phase diagram. What does it mean? It means that. Okay. Let me go to the screen first, and then my screen. So what I plotted here at temperature versus some type of like how many proton neutron are compact together. So it is basically like the early universe picture, like how it will change, and various experiment in the world actually trying to calculate this phase diagram, and it is impossible to do it by any means, and whoever will be able to calculate it nicely analytically, and there is a chance that people will get Nobel Prize because of that. So this QCD phase diagram is that important. So next, go to the next page. So people who are interested, the student who are interested to study early universe and particle physics, this is one of the like tremendous area of interest. They can join. There is analytical calculation. There is a numerical calculation, and both of these can help you to gain insight in the early universe, particle physics, and various other things. Okay, so please go to the next page. So which is showing some diagram and some actually this is CERN accelerator. Yeah, is cutting, I think. Okay, so these are, yeah, it's very bad. I don't know why PDF became also something like that. I go to the next page because it is again it is hub. Let me share once more because it is pretty. I don't know why this PPT to PDF. Maybe in hurry I have done that. Uh, what screen are you looking actually?
Nothing is seen.
Nothing is seen.
Yeah, it will come, but it is taking some time. Yeah,
Uh,
that,
Now one slide has come.
What is showing?
it's a simulation picture, I think, of LHC.
Okay. All right. And can you get the next page?
Slide number
This
কত?
particle indirect direct like this red color.
No, 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 no.
Okay, I will stop sharing because these will not work. No, one thing I can do, again make a PPT and then send to you.
Actually, Professor Mathur, actually students are waiting for interactive.
Yeah, the many things I haven't talked. I talked only astrophysics part, and then the particle physics, and then the quantum computing, then computer and machine learning. There's quite a few things done. What I will propose to you, is it possible meets another day, and I will send you a link, the Zoom link,
Okay, okay.
uh, because this WebEx, I think there is an issue either from my end or your end. Did you use WebEx like it is very commonly used, or
Yes, yes. Every seminar I organize it is through this WebEx.
how many people, like so many people, and the big files also?
No, actually, WebEx is the recommended for this. Every people actually join. I
I'm
think you
saying,
could not download this app, this apps actually. This 20 MB files apps. Through this app you enter, I think it is working okay.
I can do it even now. I mean, yeah, I should have checked in the morning. I thought this is like a Zoom meeting, and so this is
Yes,
my
yes.
mistake. This is really my mistake. Let me download it and see whether.
Okay, Nilmani, can I suggest
Yeah,
something?
yeah,
Uh, I, I may suggest one thing. If there are some question from the behalf of students, let the answer, let the questions be answered, and you may arrange on other day, or something like that, and you can send the material to Principal Maharaj also, because this
yeah.
problem is not basically from your end or our end. This is basically network problem, may arise in any platform at any time, and this is for the first time we face such huge problem in WebEx. We have arranged several meetings, but
Yeah,
in none of those meetings we faced this sort of problem. So
yeah.
our
I'm downloading the app. Just
students have
wait
given
few.
some questions.
Okay,
Okay,
so
you try to fix it
let
within 5 or 10 minutes.
let me share one screen, and that maybe student may what we wanted to, that may be helpful for them. Like,
Basically, they are getting impatient, I think.
and
about meeting another day as Professor Mathur suggested?
Yeah, so for the student, I put a want to do research in physics. That page, is it coming?
No, 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 no.
Okay.
Yeah, it has come now.
Okay.
It is visible now.
Okay. So
And,
what
and now it has come.
okay, what I will tell the student that if you want to do pursue research projects, first start to do a project with a faculty of your institute, or at other places like TIFR has this summer research student program. You can participate while in BSc itself, like in second year, from second year you can apply, uh, and then you will know the flavor of physics, flavor of research, how to do research. And then you take part in the, I think all of you know this GEST or individual institute exam. The TIFR has its own exam. It will take, I think this year will be in March. Those who, I think probably you have already registered, so registered student will be able to take the entrance exam. And for PhD, you can go to the TIFR, ISC, HRI, SINP, cultivation, math science, for astrophysics, IUCA, RRI, Indian Institute of Astronomy, etc. Or if you want, you can take GRE and go to US or Europe. For Europe, of course, you don't need GRE. And there are lots of European institute, Max Planck Institute, uh, and also some institute in France. They want many students for doing research. So you can apply. You can apply individual. Go to the individual institute homepage and ask and see the relevant people, and then write to them directly, and they can help you. And if you want to do just MSc, then also similar process, take the entrance exam. But at the entrance exam, after doing 1.5 year or 2 years MSc, you can move out to other institute, better places, or go to abroad also. So these are the two routes: either directly go to the PhD, that is integrated PhD, and or take MSc route and then go to PhD. So this is the procedure that we are following right now. Individual institute like TIFR entrance exam, you can take part. But you able to see the next page, the general advices. Hello.
No,
No, no.
sir, still not.
Okay, it will be coming. So general advices, I want to give to the student that do your coursework with attention. Maybe you are thinking, I don't want to do coursework, but it is not actually good. You have to do your coursework with attention, and solve as many problems as possible. So if you come to institutes like TFR, like that, and then we give lot of homeworks to solve. Uh, and solving problem will make you how to uh, have to think properly, like what I call the straight thinking. And most of the time we found some problem is tough. Actually, the problem is not the problem, it's the problem of thinking, how we are thinking. So try to think straight. That's why I'm telling that based on your knowledge that you already know the physics laws. There are few physics laws. Apply those in a very straightforward way. You will get, you will go to somewhere. If you find a problem is too hard, most probably it could be due to your thinking convolutedly. And read articles from journals like Nature, Science magazine. Um, Soon, I think these will be online by the government. I know that principal secretary to the principal advisor to Prime Minister, he is making these things to be available to everybody. There will be database soon. But if you do not get access from your place, try to see where can you get the access for these magazines. And these are the state of the art research comes out this magazine. The APS physics news are actually free, so you can go to their webpage and see APS physics news what are coming. These will make you aware like what's going on outside, what is up to date things. And many times we don't know what's actually the most important things are going on. So you have to be very positive to approach those, and then of course you have to try hard, keep you motivated. There is no alternative than hard working. So these are the general advices. um, and okay, so is there, let me go to whether and I can I almost downloaded it and see whether hello.
Yes, sir.
Yeah, I'm just downloaded, and um, Mind again through your that app. Hello. Hello.
Yes, yes.
Is I'm stopping video but sharing the screen, and let's see whether it anything.
Here, this optimized for text and image, it is selected.
Optimized for, yeah, it is selected optimized text and image.
Best. Now we can do this.
Can you see the sharing screen?
Yes, sir. Now it is visible.
Full screen. You do this full screen?
Yeah. Is that coming?
Yeah.
It is changing?
Yeah. It's now okay.
Is it changing?
Yeah.
Okay. I don't know for enthusiastic. I can continue, but the student will be all right, Maharaj?
Actually, the students are at 2 hours now. You can try to finish because they are teenage. Maybe they are innocent. They want
Okay.
to
So,
talk with you. Maybe very
okay.
much eager.
What we will do that yeah, this is a silly mistake from, I think, from my end. That's why it happened. I should have downloaded it in the morning. Could be that the reason, but I'm not sure also. But what I can do, I can give them another talk of the second part of topic.
Yes.
But not today, but let's say next Saturday again. Is that okay? And today we will talk with them what they're question, or any other day when they are ready.
Yes, another day. Actually, according to their convenience, because exam is coming. Maybe it's
Exactly.
another day after exam. After
So
exam.
tell you decided. Tell me, because my talk is already prepared. So whenever you tell me, I can.
Yes.
Yeah, that will
Definitely.
be.
And today I can talk with them whatever they want to know. So
Yeah.
let me
Yes.
towards the end. So what I wanted to just glimpse of them. What I wanted to talk with them. I talked with basically astrophysics. Then I want to talk on particle physics. And then what I wanted to talk, what are the unsolved problem in particle physics? There are lots of experiments going on, including in India. Then I want to talk nuclear physics, what are the unsolved problem. Then condensed matter physics. Condensed matter physics has this entanglement, which is a huge thing now. And many students, they may know well this entanglement thing. I want to discuss a bit. and then something called the spin liquid. Is the transparencies are changing now fast as I am doing?
Yes, yes.
Okay. Then nanophysics, I want to say what are the nanophysics things that I want to discuss. Something called the topological insulator. Also, I want to discuss a bit. Then one main part I want to discuss is something called the computation, which is the machine learning and the quantum computation. And what the machine learning and quantum computation are doing, I want to tell also to them. And then I wanted to show that how much computer we have in the world. This is my computer that where I work, and then I want to tell them because this so far I talked only a theory, but there is a major part which is an experiment, and the precision experiment is coming, and that will revolutionize our understanding of the world, which is called the quantum sensor. So I want to tell a little bit what is quantum sensor. So that's that part. And so I will end, but that part I will talk in some other day when they are ready, and just let me know, I will discuss. Otherwise, so conclusion is that it's a very exciting time to pursue research in physics. And I already told how you want to do physics and general advices. I will end with this quote: nothing happens unless you dream first. The task of the mind is to create future, and the future belongs to those who actually can dream. The beauty of the dreams. And you are made of stuff. The element in your atom, in your body, the calcium and other elements that in your body came from the star by the supernova explosion. You are made of stuff. So arise awake and stop until reach your goal. So that Samiji told us. So be very, very motivated, and this is an exciting time to do physics. There are plenty of areas, and current physics is really, really nice. I would end like this picture and think about it. Can you show this picture? Can you see this picture? What I saw, this is a blank screen. Is that visible to everybody?
Yes, yes.
Okay. Do you know what is this actually? Is anybody knows?
That is the means back page of Carl Sagan's book, I think. That white spot is our galaxy or something like that.
Okay. Anybody else? Any student? Okay. So yeah.
Of Earth from million from Voyager.
Yeah.
Yeah.
These are these circle, these point, this pale is called famous pale blue dot. It's a photograph of Earth taken 1990 in NASA's Voyager 1 at a distance of 3.7 billion miles, 6 billion kilometers away from the sun. See, what is that? So look again at that dot. That's here. So that's home. So that's us. So how tiny we are in the vast universe. Now think about your existence and how much do you know and what can you know. With this exciting time, you can actually learn a lot of things and contribute to the understanding of this universe. So with that, I will end and I will discuss with the student. And as I told, I will be happy to give another talk with them if they are interested. So yeah, so what is the student's question? We can interact combinedly or one-on-one.
Yeah, I think if students have any question, means already if they have asked to Professor ADC, you can also put forward the questions. And if
Actually, most of the students, I think, they have left. May I ask you one question, sir?
Yeah. Sure.
Can you please explain a little bit clearly the meaning of this cosmic microwave background? What is
Yeah.
at the temperature associated with it?
Yeah. So let's go back to So, did you see the screen, the cosmic microwave
Yes,
background?
yes.
Okay.
Yes,
So
yes.
this is like let's go. Let's you are burning something. Let's say you have a in your home the light bulb, and you put a detector. So what will detect? The photons are coming from the light bulb. So you will get the wavelength of the photon, and from there you can find out what is the temperature of the light bulb. Is that okay? Hello.
Oh, okay, okay. Yes.
Now go to the sky and put very accurate some instrument which can measure microwave. Microwave is very length this microwave wavelength. So temperature very small, and when you put that instrument, you see. So you have to get rid of all the higher like high energy particles like cosmic rays, high energy photons, like which are giving flooded everywhere. You get rid of those. Detect only very low energy these photons. What you find that from everywhere of the universe, whichever direction you put your instrument, you will see that these photons are coming. And this temperature of these photons are 725 Kelvin. So this is extremely small, tiny, like temperature range photons are coming, and their distribution is like a black body distribution. And then you like everywhere in the sky, from wherever it is coming, you map it. You have to do one-to-one mapping, and after doing this mapping, you will get this picture. And this picture is showing wherever there is a blue, very blue dot. So those are the temperature, maybe not 2.725, maybe it is 2.7 or maybe 2.68, something like that. But which is the red, so that is a little bit higher, maybe 3 Kelvin, something like that. So these are the structure. Now, from where it is coming, because you got rid of all the sources, you got rid of light coming from star or wherever you can think about it. Your instrument is good enough to detect these low things, and it everywhere. So it shows that since it is like everywhere it is, and it is uniformly distributed, isotropic. So that means it has a common origin. And it is like a blast. Some blast happened at some point of time, and that's why and the signal is coming from that blast. So this is called the cosmic microwave background. So everything is the background. Or background means is like a surrounded. These photons are full of this photon. Actually, wherever you go, you will see these photons in this universe, and they are coming. If you let me show another picture. Maybe this one. So can you see this picture like 700 million here, 3 billion here, like those type of numbers are there, the recombination, matter domination, that picture I'm talking about. Can you see it?
Okay, yes, yes. I can see it. Yes.
Hello?
Yes, you can see it.
Yeah. So
Hello.
after the nucleosynthesis, the matter domination, at some point of time, there was a period when nothing could come out. That's called dark age. But after that, light could come out, and this light is coming from there. This very early universal light is coming from. This is the photon at that time.
Okay.
So does that answer your question?
Yes, yes, yes. So can you I think there is a temperature. So can you associate some sort of entropy with it with this temperature? I mean.
Yeah. So our understanding is that like entropy increasing, entropy order getting getting much more disorder. So these there was very ordered phase at the beginning of the universe, and then so entropy there was very less, and then entropy increasing very rapidly, and one can associate an entropy with this cosmic micro background, because this has a like uh, the spectrum is like a black body radiation spectrum, so that type of entropy.
Okay. Okay.
But it is not changing. It will be changing after a long time. The temperature will come down a little bit. It will change, but that almost uniform. It is not changing very slowly. So entropy is not increasing, decreasing that much. If you associate entropy with that radiation.
Yes. Okay. That's interesting. Okay. Kullan, do you have any question from the students?
No, I think I don't have any
So I think we
from
should.
their side. They want to ask, then they can.
Kullan?
Would you like to ask anything to Professor Mathur? Yeah. Yes. Hello.
Hello. Yeah.
Am I audible?
Yeah.
Okay, so I'm asking the students if they have some questions they can put forward to Professor Mathur, or if not, then I will ask Professor ADC to give a vote of thanks to Professor Mathur.
But I'm extremely sorry that this turned out to be like this. I wanted to actually interact with the students also, but I think after their exam or whenever, if they want to talk, the remaining
Yeah,
part of the
we can arrange that thing. Means the problem means this type of technical glitch happens sometime, but it's not in our hand and in your hand either. So it can, no one can do something in this thing. So better we can arrange one another schedule so that
sure.
you can deliver what you wanted to say to the students. So better we can stop here, because most of the students maybe they have left already. So
Okay, let's.
I think Professor Office Dipankar Chakraborty. So you just you just give a vote of
Well,
thanks.
a very good evening to all of you. Due to technical glitches, as Kullan has mentioned, session has really lengthened beyond 1 hour, because that was not in our hand. And prior to winding it up, I would like to propose the vote of thanks to all who have helped us in making this seminar a success. First of all, on behalf of the principal of our college and the faculty members of physics department, I'd like to propose the vote of thanks to the speaker, Professor Nilmani Mathur of TIFR, for his presentation. Though it was really interrupted many times due to technical difficulties, but I think he is able to give some flavor of current modern day research in high energy physics to our students. And I would like to thank our principal and head of the department for their support and guidance. And once again, I thank you all for your kind cooperation. So thank you. Thank you.
Yeah, thanks to all. Again, my apology that it didn't turn out well.
Hello, Nilmani.
Yes, yeah.
Please visit our institute, our college when the situation is normal.
Yeah, sure.
As a friend and to deepen our old friendship, revive
Yeah,
that
yes.
one.
Yeah, sure. Absolutely, no
I would
problem.
expect you when you come to Calcutta. Please inform us. We will arrange to take you over our
Yeah.
college. Okay. Good evening.
Yeah.
Thank you.
Okay, good evening.